C'est mieux là? Okay, so Laure did her PhD on kinetic theory of gas with François Goll at Paris 7. She then became a CNRS researcher for 2 years, and then a professor at Paris 6 and ENS after that, where she served as a deputy director, in particular of the Department of Mathematics. She then moved to ENS-Lyon. Laure is also a member of the Académie des Sciences, as you may know. She was elected in 2013. She's also a member of the European Academy of Sciences. She's also a Chevalier de la Légion d'honneur, and she has been awarded many prizes. So I can't say all of them, I guess, but just to name a few, she got the Prix Louis Armand of the Académie des Sciences, the Ruth Little Satter Prize of the American Mathematical Society, Prix Irène Joliot-Curie de la jeune femme scientifique, Prix Fermat de l'Institut de mathématiques de Toulouse, etc., etc. And very recently, she got the Butcher Prize of the American Mathematical Society, and maybe I should cite the press release, for her transformative contribution to kinetic theory, fluid dynamics, and Hilbert's 6 problem. So indeed, Laure is an expert of partial differential equations and their application to fluid mechanics in particular. She, for instance, studied the Boltzmann equation, and also she worked on geophysical problems, and I guess this is the topic of the talk today. So thank you very much, Laure, for being here, and the floor is yours. Thanks.
Okay, thank you very much for the introduction and for the invitation. So as you understood, I'm not an astrophysicist. I'm not even a physicist. I'm just a mathematician. But I will try to explain some, some tools that maybe could be useful also in astrophysics. Okay, because essentially what I will try to explain is how you can separate phenomena at different scales. Okay, so this is the main goal that I would like to achieve today, is to try to give you a very broad overview of things that we can do with this kind of methods. Okay, so here what I will discuss is not exactly related to astrophysics, even though I think that this kind of internal waves are also important in the core of many planets, or probably, okay, so for the application I let you. So what is typical from geophysical fluids, say compared to usual fluid that you can just have in your bathroom, is that you have a very strong anisotropy. Okay, and this I think is really important. And actually, there are many sources of anisotropy. So if you think about the ocean on the Earth, the first reason why you have a strong anisotropy is just the aspect ratio. So if you look at the depth compared to the horizontal extent, this should be exactly the same as for just a sheet of paper. Okay, so the same kind of aspect ratio. So you see that really this is almost 2D. Okay, then there is another. So even though you consider the vertical dimension, there is another source of anisotropy which comes from the fact that you have a very strong stratification of the fluid, meaning that the density above is much lighter than the density in the deep ocean. Okay, so this is another reason why you have anisotropy, and this will be responsible for this internal wave that I will discuss a little bit at the very end, because here I will mainly focus on the third source of anisotropy, which is rotation. Okay, so as you know, of course, you have a very strong effect at the large scale. For the large scale flows, you have a very strong effect of the Coriolis force, and this is what I would like to discuss. So starting from a model where you say written all the physics of the system, so not all, but say you start from a general model of fluid mechanics, and then you assume that this effect of rotation is very strong, so because just the parameters, physical parameters are such that this is the dominating force, and then you can extract from this model some simpler models where you can just separate the things which happen at different scales. Okay, so the equation that I will discuss, but I will try not to give you too many formulas because this is not really important and this is not really what I would like to discuss, but So here I will start from, say, the main equation in fluid mechanics for incompressible fluids, which is the Navier-Stokes equation, plus here the Coriolis force. Okay, so here this is just the time derivatives. Here you just take into account the fact that you have convection. Okay, so this would be just the acceleration of, say, a particle of fluid that you just follow here. Then you have this term here, which comes from the Coriolis force. So this is the rotation of the Earth. Then you have the pressure, okay, and the pressure will be another unknown, which will be completely determined by the fact that the fluid is incompressible. And then you have the viscosity here. Okay, so at the scale of the ocean, actually the viscosity is very, very small. Okay, and so then you have that the pressure here is prescribed by the fact that your fluid is incompressible, and so you have that the divergence of the velocity field is equal to 0. And then you have boundary conditions, of course, and so boundary condition, it will depend on, say, if you are on the bottom or on the surface, but say there is one which is really important, which has you have zero flux. Okay, the fluid is not going out of the ocean. And then, say, usually you assume that at the bottom you have just 0, which is friction, okay? And here you have a condition on the surface, which is due to the winds. And so this gives you this condition on the vertical derivative of the horizontal velocity. Okay, so this is the model that I will discuss in the sequel, but okay, once again, what I really would like to do is to try to explain these different tools that you can use to understand, say, the phenomenology of the system. Okay, so the first thing that I will discuss is the separation, so between a mode which is called geostrophic, which essentially for which you have a balance between pressure and Coriolis force. And then say the perturbation with respect to this kind of equilibrium is given by waves, okay? And this is here the inertial waves, okay? So I will try to explain later on why internal waves, so due to stratification, are very similar to these inertial waves, but say most of the time I will discuss these inertial waves because they have many important features, okay? So what I say is that if in this system the dominating force is the Coriolis force, then in the equation what you have to written as main terms, so of course you have still the incompressibility condition, okay, your fluid is still incompressible, so you keep the fact that the divergence of u is equal to 0, and then in the other equation, in the equation for the evolution, the main terms are this term here, which is the Coriolis term, and of course you still have to keep the pressure term, because this is something which just ensures that you can keep this incompressibility condition. Okay, so this pressure term, a priori, is, say, very strong as well. Okay, and so geostrophic means that you are exactly in the what we call the kernel of this linear operator here. So this is equal to 0 and this is equal to 0. Okay, and so this is the balance between pressure and rotation. And so now, if you compute this, if you look at you write all the equations which are associated to this, what you get is actually that the solution to this equation are 2D flows. Okay, so this tells you that even though you start from a fluid which is 3D, and I forget about the fact that I have this aspect ratio which is very small, so even in another domain, if you have this Coriolis force which is really important, then what you see, and there are many experiments maybe that you know, for instance, on the Coriolis platform in Grenoble, okay, where you can see this kind of thing. So if you have a very, very strong rotation, then what you see is that the flow will be 2D. Okay, so in particular, if you put an obstacle here, just on the bottom in your experiment, you will see that you have what is called Taylor-Prudman columns, and they will just go around the obstacle. Okay, so even on the surface, you will see that if you put a little bit of color, you will see that these columns will just avoid the obstacle. Okay, so this is something that you can obtain in a very simple way, just by looking at this main, so the dominating terms in the equation. Okay, so this is for the part which is at equilibrium, and then of course you have fluctuation around this. Okay, so if you start from a data which is not well prepared, so which doesn't satisfy this constraints, then you have fluctuation around this state, and this corresponds to what is called inertial waves. And so this is the equation that you obtain. So dtu is now the time derivative. 1 over epsilon. Epsilon is small, and it's the Coriolis. So what is called the Rossby number. It's very small. Okay, it measures the strength of the rotation. And then, so what I have written here is maybe a little bit not usual. So here this is the Coriolis force, but now I project this on a field which are divergent free. So this is another writing for U wedge E3 plus gradient of P. Okay, so all of this is a projection on field which are divergent free. And so now the equation is this one. So you see that's an equation of the form dtu plus 1 over epsilon times an operator which is linear equal to 0. And this operator, what you expect is that it's a skew-symmetric operator, so it will just generate something which is an oscillation. Okay. So now if you have this oscillation, so now if you have in a very simple domain, so for instance just a rectangle with boundary which are parallel to vertical and horizontal, okay, then what you obtain is that you can compute this. You see that all the coefficients here are constant, okay, and if you have a very simple domain, then you can use a Fourier transform. And then you can, so this operator, which is what is called a pseudo-differential operator, you can express it in terms of the Fourier number. Okay, so I think you say wavelength or wave. Yeah. Okay, and what you get is the dispersion relation for these waves. And so you see, what you get is that the frequency, the temporal frequency, will be equal to plus or minus k3, so the vertical wave number divided by the modulus of k, which is the total wave number. Okay, so it is very different from, say, more usual waves such as acoustic waves or electromagnetic waves. So for usual waves, you have that this omega depends only on the modulus of k, while here you see it's very different. It doesn't depend on the modulus of k. It depends only on the direction of k. Okay, and so this will, I will come back on this later, but this tells you that if you just think about it in terms of plane waves, you will have a propagation for this plane wave which is very, very different from, say, acoustic waves or electromagnetic waves. Okay, so I will come back on this later, but okay, say at this level, what you know is that you have, you can write all the solution as a superposition of plane waves with this dispersion relation. Okay, and so you have oscillations, and you can. Okay, so this is what is called inertial waves, and so even in a very simple geometry where you can use this Fourier transform, then the next step, if you would like to characterize the motion of your fluid, is to understand the effect of the nonlinear term, and so this is something I think which is interesting because it's not. I think it's very classical in mathematics, but I'm not sure that it's classical for maybe in astrophysics. So the way you look at, so you have all these waves, and then you have a coupling of these waves by the nonlinear term. Okay, and so the usual way to look at this is, I think this is what we do for just to look at this interference figure and so on, the pattern. So you just try to say it maybe. So what we say is conjugate by the group, which is so these waves. So another way to say that is that you try to look at the envelope equation for these waves, and you will have a slow evolution of the amplitude of each wave, and this will be governed by resonances of these waves. Okay, so resonance means that you will have two waves with wave number k and l, and they will be resonant if this frequency here is equal to plus or minus the sum of these two. Okay, so this is the notion of resonance, and so this tells you that you can write also the slow evolution. So you see that at first sight, what you get is that the the perturbation is given as the sum of waves, and then what you do here is to try to find the amplitude of each wave, and what I say is that you have a slow evolution of this amplitude, which is completely determined by this resonance system. Okay, so this is only if you would like to go, say, further in the description of the system. Okay, so essentially I will not comment more on this nonlinear things later on. What I would like to discuss now is the effect of different geometries. Okay, so I will stay at the level of waves, and I try to understand the level, the effect of geometry. Okay, so one very important thing, okay, especially for the dynamics of the ocean, is what is called the Ekman pumping. So I will try to explain what it means. So if you remember what I wrote on the very first slide, I told you that, okay, you have this basin, which I assume for the moment to be just a parallelepiped, okay, so with a bottom, a surface, and I just forget about the lateral boundaries. Okay, so in this I can of course use the Fourier transform up to some. So I have here the right dispersion relation for the wave. But now, of course, you see that if I look just at the geostrophic constraint, at the geostrophic equilibrium, you see that what I told you is that at equilibrium, what I should see is something which is purely 2D. Okay, but now you see that if you require that the velocity field is purely 2D, and that you ask that on the bottom it's 0, and that on the surface the derivative is not 0, you don't have any solution to this problem. Okay, somehow it's overdetermined. Okay, because it's not possible to satisfy both this geostrophic constraint, which impose that you have something which is 2D, and to satisfy the boundary condition on the top and on the bottom. Okay, and so this is why you have this boundary layer. So this means that, say, close to the surface and close to the bottom, what you expect is that the velocity field will fluctuate very rapidly. Okay, and in this small layer, what is important is viscosity. Okay, so viscosity usually is very small, so you don't care about it. Okay, but say in order that you can impose this boundary condition, actually viscosity is really important. You see that if you add viscosity, essentially you have a system of equation of order 2. Okay, so say the main order derivative are of order 2. Okay, while and so you can impose more boundary condition that if you have just this rotation, which is of order 0. So essentially you cannot impose any boundary condition. Okay, so this is really important that to understand that viscosity, even though it's very small, it will play a very important role close to the boundary, close to the surface, and it will be really important because this is how you can transfer some energy from the atmosphere to the ocean. Okay, so also it's very localized. It's really, really important to understand the transfer of energy. Okay, so what you expect is that in this small layer, you would like the viscosity, which is like nu times a derivative of order 2, is of the same order as the Coriolis force, which is 1 over epsilon times u. Okay, so essentially you have that two derivatives will be of the order of 1 over epsilon u. Okay, so this is how you get here the fact that the size of this layer are like square root of epsilon u. Okay, so this is just because you try to equilibrate this viscosity, the effect of viscosity and the effect of the rotation. Okay, and so then you can just look at the two important terms in the equation, and you get here this term which comes from the rotation, and here this term which comes from viscosity, and of course only the derivative in the normal variable is important, and so you get that the profile in the boundary layer should satisfy this equation here, so you get exactly this exact form for the profile in the boundary layer. Okay, so now you, so assuming for the moment that I have no fluctuation, so no waves, what I say is that the solution should be the sum of the 2D profile plus this small boundary layer close to the surface plus this small boundary layer close to the bottom. Okay, and these boundary layers are of size square root of epsilon nu, and the profile is given by this. Okay. So, but now if you construct just this, you see that you have some troubles because then you have the divergence-free constraint is not satisfied anymore, so you have to restore this divergence-free energy constraint. So this tells you that you have also a very, very small, in the boundary layer, you have a very, very small vertical component. Okay, but then you see that if you have a very small vertical component, then the zero flux condition at the surface and at the bottom are not satisfied, so you have to add another correction here to restore the zero flux condition. Okay, so once you have done all this process, then you see that essentially you get now a solution which is this 2D plus the two small boundary layers plus a very, very small vertical flux. Okay, so the right approximation here will be the sum of these three things, and this small vertical flux, which is what is called the Ekman pumping, which tells you that actually you transfer energy. So now you see that essentially you have that the effect of the bottom will be just like a friction now after this Ekman pumping, and the effect of the wind will be just like a source. Okay, so what you are able to do with this boundary layer techniques is to transform an equation which is 3D, and you know just constraint on the surface and on the bottom. Okay, so it's really 3D. You can, and then you can transform this in a simplified model where you have a 2D model, and you are able to transform the constraint on the boundary in source terms or friction terms in the equation. Okay. This one? Yes. So this delta WH is a horizontal component. Ah, okay. So because you have to add everything add in order that everything is divergence free. Okay. But so what is really important is that, say, okay, you have a lot of computation here and it's a little bit technique, but the important thing is that with this very systematic process, what you are able to do is to transform this 3D problem in a 2D problem where you have really integrate also the constraints on the boundary. And this is really important because this is completely systematic. You don't need to assume that this or that. This is a very systematic way of transforming your strongly anisotropic system in a 2D system. So what is pumped is, so if you just look at the effect of the bottom, so you have this Dirichlet condition, so that U is equal to 0 on the boundary, on the bottom, okay? And say what if you write now the equation on the 2D field, so this average thing, what you get is the equation is dTUH will be equal to minus 1 over square root of 2, so 2 is not really important, UH. Okay, so you have this effect now is really a friction, and so it will really remove some energy from the fluid. Okay, so this is why it's called pumping, because of the friction on the bottom, you really remove some energy from the fluid. And actually, say usually for this part, so Ekman pumping is this part related to the bottom, and usually this part which is related to the wind is called Ekman suction. Okay, so you extract energy from the atmosphere and just inject it in the. Okay, so I think it's really important. Maybe at some point you saw a picture like this, and this is also maybe just for the later story. This Ekman pumping was discovered by Nansen, which was an explorer in the North Pole. And actually the point, the way they discovered this is that they realized that if you look at the motion of the icebergs, actually they deviate from an angle of approximately 45 degrees compared to the direction of the wind. So if the wind blows like this, the iceberg will go like that, which is a little bit surprising. But actually this is due to the fact that the iceberg is mostly immersed. Okay, and then you see that in this boundary layer, the velocity will change very rapidly. And so the velocity a little bit under the surface is not in the same direction as the velocity on the surface. Okay, so this is the way this Ekman pumping was discovered, I think, 1 century ago. Okay, so this is the first thing that I wanted to discuss, so the fact that you can really integrate this constraint on the bottom and the surface in a 2D model, which is really important. Okay, now there's another thing that I would like to discuss, because maybe it's less known, and I think it's really important because it can be used in many situations, even though it's not a fluid and so on. Okay, so now the point is the case where you cannot choose, so you have a more complicated geometry, and you cannot choose, or you have a rotation which is not constant. Okay, of course, you see that here, for the moment, I have assumed that the rotation is constant, but of course, you know that if you look at the scale of the Earth, okay, now actually what is important is not the rotation of the Earth, but the projection on the vertical of this rotation vector, and of course, it will depend on the latitude. Okay, so what I told you here is a very simple model where say the rotation is constant, but now here you see that, of course, if you look at, say, something which is locally horizontal, of course you see that the projection on the rotation vector on the local vertical will not be constant. Okay, so now I would like to understand different, say, more complicated models where either the rotation is not constant or the geometry is more complicated than just a parallelepipedic box. Okay, because say this is not exactly the geometry of the ocean. Okay, so the first thing that I will discuss is this inhomogeneous rotation, which is of course important, and we will see that this will generate very important effects close to the equator. Okay, so this is probably what is written here. So now if you look at the say locally the rotation vector, you see that it depends on the latitude. Normally it should be something like the sine of the latitude, but here I will simplify this and just assume that say the vertical component of the rotation is like beta times x2, and x2 is just the latitude. Okay, so this is very standard approximation of the sine close to 0. Okay, so this is what is called by geophysicists beta plane approximation, and it's particularly important close to the equator. Okay, so now if you go back to the very first slide, so where I say that, okay, now if I try to understand the motion of the fluid, I will decompose it as one component which is at equilibrium, which is called geostrophic equilibrium, plus some parts which are oscillating, which are called inertial waves. But now you see that it's more complicated because, so you have so the operator, I can maybe write it. Okay, so the operator is still, so it's U, so the operator is U wedge E3, but now instead of being this, it's U wedge E3 times beta x2, okay, because now this is not a constant, okay, so I multiply by this scalar here, plus gradient of P, okay, and this has to be a divergence free. Okay, so this can be also rewritten, the Laure projection of U dot E3 times beta x2. Okay, so now you see that there is something that I cannot do anymore, is to take the Fourier transform of this guy, because if I take the Fourier transform of this guy, you see that I have multiplication here, and so this will be transformed in something which is a convolution of the Fourier coefficient of this guy and the Fourier coefficient of this guy, and then this is just a nightmare. Okay, so what it tells you is that if you have non-constant coefficient, Fourier is not the right way to study this kind of operators. Okay, so and this is of course a problem, because once you can use Fourier, it's really easy, because you just replace all the derivative by multiplication by the wave number, and then you can compute everything just by I don't know, something like diagonalizing a matrix 3 by 3 or something like this. So it's something that you can really compute everything. So now what I say is that you cannot compute. Okay, so actually here, with this specific choice of the coefficient, it happens that you can still do something which is explicit, but we will see that this is kind of exceptional. Okay, so here, because of this particular form of the coefficient, what you can do is to use, so still the Fourier decomposition for the for x1. Okay, x1 you have no specific occurrence of x1 here, so the coefficient doesn't depend on x1, so you can use Fourier in x1. But in x2, what you will have to do is to use the Hermite function. Okay, so the oscillator, the harmonic oscillator, and it happens that actually in this specific basis, then you can diagonalize the operator, and then you get. We will see that we can obtain a very precise description of this operator, except that instead of having everything in the Fourier basis, so I recall that in Fourier, what I get is the spectrum as just a collection of this guy here. Now it will be more complicated, but it will be, you obtain a basis, so you obtain a collection of eigenvalue, which will depend on k1 and n, where n is just the quantification of the oscillating, the harmonic oscillator. Okay, so, but you see that there is something which is very different here, that, say, the right basis here will be expressed in terms of this Fourier modes, and in terms of psi n of x2, and these are the Hermite function, and the specificity of the Hermite function is just that they are just like exponentially decaying at infinity, and so you see that the waves, they will be localized close to the equator. Okay, so you really find that the equator behaves as a waveguide. Okay, so it's really important because if you look at some map of the Earth that you obtain by satellite, you will see that you have very important currents close to the equator. Okay, so this is not something which is random. It's really related to this. Okay, so but you see that here it's a little bit like I'm very lucky because I have this specific expression for the coefficients, and in general this is not true that I can find an explicit solution and an explicit basis to diagonalize my operator. Okay, so this is really kind of exceptional, and this is the same for the case of Fourier. Okay, so now what we would like to understand is it possible, if I have non-constant coefficients, to still say something about the fluid? Okay, and so actually we have this method, and this is something which is strange because actually this kind of methods have been developed by physicists, but of course in a very different situation for quantum mechanics. Okay, but still, say this is a very powerful tool to understand how you can extract different scales, so a fast scale and a slower scale. Okay, and so here actually this semi-classical analysis can apply, and it's even though you cannot compute explicitly solutions, even at the linear level, you will be able to say a lot of things about their behavior. Okay, so this is really the idea here, to use the fact. So the man, I will not, of course, give now a course about symbolic calculus and all these kind of things, which is rather complicated, but just to give you a little bit of intuition about this. So what you say is that, of course, the coefficient will depend now on x. Okay, so you cannot use Fourier, but still, what you expect is that in most cases, actually, what happens is that, say, the wavelength of the wave that you are interested in is much smaller than the typical length on which the coefficient will vary. Okay, so you have this scale separation between the wavelengths of your inertial wave, say, and the typical scale where you have a variation of the coefficients. Okay, so now you say that, okay, now what I can do is to say that I have two scales. So this scales x2, which is the scale where I see a variation of the coefficient. And now if I look at this internal wave, inertial waves, what I know is that actually the wavelength is much smaller, and so something of the order of 1 will be not d2 but epsilon d2. Okay, because you have this scale separation. Okay, so in quantum mechanics, of course, this epsilon is just h bar. Okay, and so what is of the order of 1 is, so you have 2 here. So of course, normally you cannot say that x2 and epsilon d2 are two things which commute and which live independently from each other. Okay, but actually here you see that if it's really epsilon d2, you see that if you look at the commutation between these two things, of course it's not 0. Okay, what you would like to say is that now you have two different variables, x2 and xi2, and you would like this to be two independent variables. So it's not true that there are two independent variables, because if you look at this guy, of course, it's not independent from this one. But if you look at the commutation between these two, what you get is something which is smaller. Okay, and so this gives you, say, a systematic way of doing asymptotic expansion. So you exactly do as you have two independent variables here. You compute everything. So now you see that you can replace all derivative by just multiplication by xi, which is exactly like in Fourier. Okay, and so now you can compute everything. You are really happy with this. But of course, you will do an error doing this, and then but this is an error which which is at next order, and so you can compute the first order just by doing as these two variables were independent, and then you say, okay, now I have a little bit of error, but this is not a problem. At next order, I will correct this error. Okay, and so you have kind of systematic way of expanding the solution. So first, using this two variables, so now you have, so instead of one variable, you have two. Okay. So this is what you obtain, and so for instance for this problem here, what you get is this, that you have beta x2 squared, so this is now the Coriolis parameter, times k squared, and so you will recognize a little bit what we obtain. So just forget about this one for the moment. You see that you obtain that lambda square, which was omega square in the previous transparency, is equal to the ratio between this guy, which is k3 square, sorry, it should be a square, divided by k square. Okay, so in the case where this doesn't depend on x2, you find that this is exactly the same dispersion relation as previously. But now when I say that you have this correction here, which comes from the problem commutation. Okay, so you can really obtain all this, and so what you conclude is that instead of having a geostrophic equilibrium, you have very, very slow kind of waves. So you have two types of waves. You have waves which are the same as previously, so all these inertial waves, also called Poincaré waves. And you have another mode which is much slower. And this mode, for instance, is responsible for the creation of big vortices close to the so you can see them close to Florida, for instance. You have big vortices, and this is really the interaction of these slow modes, which are called Rossby modes, with the main current. Okay, so this is really important. This kind of method, you can really say something even though you don't have explicit solution. So this is maybe the most important thing that I would like to share with you today, that even though you don't have explicit solution to a mathematical equation, it's not a problem. You can say you can derive a lot of features of this solution, even though they are not explicit. Okay, and so here what I say is that, okay, you cannot diagonalize your operator. You don't have a nice basis of eigenfunction for your operator, but still you can say a lot of say about the phenomenology just using this kind of semi-classical analysis. Okay, so in the case of so now you have so this is the new formula for the dispersion relation. Of course, it's a little bit more complicated, but still this is. And so you see that you have these two kind of modes. So the modes which are the same, so just the extension of these Poincaré modes that we already saw in the previous part. And then instead of the mode 0, so you don't have this 0 mode, because this is never 0. Okay, so you get something which is so this small shift here is responsible for these Rossby waves. Okay, and they are really different. So this is called, since they somehow a bifurcation of this geostrophic equilibrium, they are called quasi-geostrophic motion. Okay, then you have that, say, at leading order, the frequency for this mode is this one, and you see that you don't have the same homogeneity. So for very large k, this is very small. It's almost 0. Okay. And so these are really, these waves have really a different phenomenology. They propagate only eastwards, much slower, and they are responsible for this oceanic eddies. Okay, so this is the influence of inhomogeneity, and I think I still have something like 10 minutes to. The last thing that I would like to discuss is the influence of topography. So now I come back to the case where they said all the coefficients are constants, but now I have a domain which is more complicated than just a rectangle or a parallelepiped. Okay, and I would like to say. To understand what is the extension of this kind of diagonalization of the linear part of the operator. Okay, so actually this was something that I was really interested in because of this problem. So for a long time I studied this problem of large rotation, and then when I arrived in Lyon, I realized that, there were many experiments in the physics lab, not about inertial waves, but about internal waves, and actually they are almost the same. So maybe I can just tell you. So if you have, so internal waves are due to stratification, so the combination of gravity and stratification. And if you do all the computation, I will not explain how you get them, but say instead of this, what you get is kh divided by k for the dispersion relation. So if you are in the torus, or in something periodic, say, or in this parallelepiped box, you get almost the same dispersion relation, except that you have to just move your head like this, okay? Okay, if you are in 2D, you see that here it's just k1 divided by modulus of k, and here it's k3 divided by modulus of k. So I'm just up to a rotation of 90 degrees, it's exactly the same. Okay, so that, so both these families of waves are very similar, they are very similar features. And so there is this experiment in the physics lab where they have internal waves, and they generate internal waves in a basin which is like this. Okay, so essentially their basin is like this. Okay, so it's a basin like this, you have stratification like that, and then they just introduce this part here, a slope which can be different, and then they see something which is completely different. So this doesn't. So the stratification?
No. The picture.
This is like so. In the case of internal waves, their picture is like this. But actually, this is not really important. So they have stratification like this, and they just instead of having the rectangle, they just have this. Okay. And so, so what they obtain, I will show you some pictures. Is that so they force the waves in this basin. So what you would expect if you have a spectrum like this is that either you force on an eigenfrequency of your operator, and then you will see that the amplitude of the wave will grow like t, and then the energy will grow like t squared. Of course, but after a while you completely destroy the stratification, and then the experiment just stops. But say what you expect is something like this. Okay. And if you force on the frequency which is not on the spectrum, so which is not of this form, then what you expect is that essentially nothing happens in the basin. Okay, you force, but this is not an eigenfrequency of your wave operator, and then essentially you cannot inject any energy at this frequency in the system. Okay, so this is what you would expect. Okay. So, so what I say is that if the spectrum of the operator was something like this, yes, what I would expect is that k is finite. Okay, so this is so the way they force is that they have a kind of motor here, and they know k and they know omega 0, and so they know everything. Okay, and what I say is that if the spectrum was something like this, what I would expect is that I have some resonant modes and some modes which are non-resonant, and that's it. Okay, and this is not absolutely different from what they observe, and I will show you some picture that actually when they force, they can force at any frequency, and what they observe is that all the energy of the system will be close to a pattern like this. Okay, so they can change the signal here for the forcing. They can change omega, and so they will change a little bit this pattern here. But what they observe is that, say, here essentially nothing happened. Okay, and close to this, you have very, very important gradient of density and very, very important velocity field. Okay, so all the energy will be concentrated on some very, very thin pattern. So then you have more complicated ones, but so essentially what they say, the conclusion is that probably you don't have the spectrum like this. Okay, so just the fact that we change the geometry will completely change the operator. And I think it's really something important to have in mind is that, okay, most of the time when you have an operator, you do this Fourier, and then you say the spectrum will be like this or like that. But just changing the geometry, it can be completely different, okay? So the point is, this is related actually at something that I mentioned at the very beginning. So compared to usual waves, so I call usual acoustic and electromagnetic waves. So for these waves, what you know is that omega is like the modulus of k. And so you know that if you look at the geometric optics or WKB approximation, I don't know how you call this. So what you expect is that your wave will propagate, of course, straight. And then on the boundary, okay, so for a usual wave, what you expect is something like this. So if you have a boundary like this, you have your wave, okay, and then it will be reflected like this. Okay, and you can, and the way you obtain this condition here is that you say that the frequency should be the same. Okay, so this fixes essentially the modulus of k. Okay, and then you say that if you project on the boundary here, of course it should be 0, for instance, and then you have no choice. You know that, say, the reflection of these waves will be this one. Okay, so now what I say is that for these very strange waves, so where omega not depends on the modulus of k but on the direction of k, the rule for the reflection will be completely different. So it will not be different in the case of vertical or horizontal boundary, but say for a sloping boundary like this. So you see that essentially what is fixed by omega here is the angle with the horizontal here. Okay, so this means that when you have a reflected wave, so this angle should be preserved. Okay, so essentially the reflected wave will be something like this. Okay, so the angle here should be preserved, not the modulus, the angle. Okay, and so then you have also the condition that if you project on the boundary here, it should be the same. Okay, so you see that if I take something like this, this will be, okay, the k after the reflection will be something like that. Okay, so what I say is that when you have a reflection for this kind of anisotropic wave, then you have a kind of focusing mechanism. Okay, or defocusing, depends on the boundary, of course. Okay, and this is so if you just look at the geometric approximation, so WKB, which is related to the semi-classical setting that I just mentioned before, then you see that you can try to do this. Okay, you can say I start with a wave. So here it's really simple because this is the usual reflection. But each time I will hit this guy, I will have something like this. And then you see that you can start from any point in the basin. Just do this ray tracing, and then say in the end you always end with this attractor here. Okay, so what I say is that because of this strange rule of reflection, just looking at the geometric optics, you see that you expect a different behavior of waves. Okay, so you have this concentration, and you see that this is experimental, this is numerical, and actually this was very surprising for us because okay, we are not physicists, so even though you see something in the basin, you need an explanation. If you are a mathematician, you need to understand this kind of thing. And so what we did is to try to understand what it means on the spectrum here. And actually the point is that instead of having a discrete spectrum like this, what you end up with is with a continuous spectrum. Okay, so now just the fact that you change the boundary, instead of having, you know, an operator which is just can write, so that you can diagonalize, say that you have a family of eigenvalues and with a family of eigenvectors. Now it's different. You have a kind of continuum of, so the spectrum is really continuous. And this means that actually what you have is that if you just look at the solution of the equation, so if you are just looking at this, so you try to find the eigenvalues here, so I can also call it omega. So this is the equation that you would like to solve. So what I say that you can solve this equation for an infinite number of omega, but the problem is that all the u that you will find, so the u omega here, they have infinite energy. Okay, so you can think about this exactly as Fourier in the Wood space. So of course, if you look at the Laplacian of psi is equal to I omega psi, and you look at this on R, you see that of course you have the same. You have this is continuous Fourier on the. So this is maybe not surprising for people just because this is a Wood space, and you say, okay, you have infinite energy. Here it's more surprising because now you see the domain is finite. Okay, but still you have continuous spectrum, and actually what you obtain is that the solution of this equation have infinite energy, and actually they diverge close to this guy here, so they behave like one over the distance of to this attractor here. Okay, so you have really a different. This is really a different representation of the operator. Okay, and I think it's really interesting. So both because we understand that there are resonance, non-resonance, but you have also something which is called quasi-resonance, which is what you obtain when you force inside the continuous spectrum of this guy, and this leads to a different mechanism. And the other point is, I think it's quite interesting because it gives you an example of turbulence which is completely linear. So you see here, what you do is that you force your system with a very nice forcing, which is monochromatic and so on. So everything is nice. And in the end, you end up with something which has very, very small scales with a very strong singularity here close to this pattern here. So I think it's interesting because, and then you can, of course, you can add viscosity, and then you get exactly what you have in mind when you talk about turbulent spectrum. So you have that, you have a cutoff which is due to viscosity, but then you have all this inertial range, and you really see a cascade from large scale to small scales, but just everything is linear. The only mechanism which generates these small scales is the focusing on this slope here. Okay, so you see that even at the linear level, you can have really a very large diversity of behaviors just depending on the geometry, the boundary condition, the fact that the coefficient can vary and so on. Okay, so I think it's important to know that also you have a very, of course in all these situations you don't have any explicit formulation for the solution. You can say a lot about the qualitative behavior of the solution. Okay, I think it's time to stop, and I thank you very much for your attention.
Cette configuration-là, il y a des exemples pratiques, physiques, avec des...
De ça?
Oui.
Alors, il y a même des exemples en astrophysique. Maybe I should... is it okay if I switch to French? For everybody? Yeah, okay. Donc, il y a des exemples. Donc, on travaille là-dessus avec Michel Rutter, qui est à l'Observatoire de Toulouse. En fait, c'est pas cette géométrie qui intéresse les astrophysiciens, c'est plutôt une géométrie comme ça. Quand on regarde dans le noyau des étoiles, en fait, on a des ondes internes aussi parce qu'on a de la stratification ici dans la partie qui est liquide. Et en fait, comme on brise la symétrie, alors si on n'avait pas de noyau dur ici, on n'aurait pas de problème, on écrirait des solutions explicites avec des modes sphériques. Mais dès qu'on a un noyau dur, on brise cette symétrie. Et donc tous les cas où il n'y a pas de symétrie particulière, ce comportement-là est très générique. Et donc il n'y a pas de mode propre, il n'y a que du spectre continu. Et donc ça, je crois que pour les astrophysiciens, c'est un peu le drame, parce que ce qu'ils arrivent à mesurer, c'est des spectres. Et là, ce qu'on dit, c'est qu'il n'y a pas de... n'y a pas de spectre particulièrement pertinent, puisque c'est du spectre continu, quoi.
J'avais une autre petite question. Si bon, j'avais une autre petite question sur quand tu fais les développements asymptotiques, là, en fonction de la perturbation, là,
Ouais.
epsilon, c'est fait pratiquement à quel ordre? C'est juste pour avoir le comportement asymptotique qui est à tous les ordres, ou bien c'est fait pratiquement à un certain nombre d'ordres? Quelle est la complexité du calcul algébrique ici?
Alors, ça dépend lequel. Donc, si on veut juste regarder, par exemple, le problème de résonance, donc l'influence du terme non linéaire, on peut faire essentiellement à tous les ordres. On regarde ce qui est résonant, puis on regarde. Ça marche comme CAM, quoi. Il n'y a pas de difficulté. Dès qu'on commence à avoir des termes de couche limite, en fait, il y a des ordres où on n'arrive pas à aller plus loin parce que les choses sont plus bien ordonnées, quoi. Donc, dès qu'on commence à regarder les choses comme Ekman, on sait le faire, on sait faire les premiers ordres, et puis au bout d'un moment, on n'a plus de, on sait pas faire à tous les ordres. C'est plus compliqué. Donc, traiter les non-linéarités, on sait le faire de façon itérative, mais la construction de couches limites est plus compliquée. Et en particulier, on se retrouve... alors peut-être que ce que je devrais dire pour être plus exact dans le cadre des non-linéarités, après, si on veut faire vraiment des développements à tous les ordres, il y a des problèmes de petits diviseurs qui arrivent. Donc voilà, il y a toute une technologie qui est plus lourde, mais en pratique, on peut le faire. Sur les couches limites, on est un peu bloqué. Et après, surtout, ce qui est analyse semi-classique, donc en principe, l'analyse semi-classique, c'est pareil, on peut étirer les choses autant qu'on veut, hein, jusqu'à des restes qui sont exponentiellement petits. Sur ces trucs-là, c'est un peu plus nouveau, donc pour l'instant, c'est un peu prospectif, quoi.
So in your dispersion relation, like omega goes like K3 over mod K, can you say what sets the scale? Because K3 and K have the same dimensions, and omega should have the dimensions of 1 over time. So what is the scale?
Oh yes, because there is this Rossby number missing. So I know this is a very...
But isn't the Rossby number also dimensionless?
So K3 divided by K has no dimension, and Rossby number has the dimension of 1 divided by time. This is dtu plus Rossby number time u wedge E3 is equal to 0, and so essentially you just have to multiply this guy by the Rossby number.
Just a clarification, I didn't understand at the end of your presentation whether you were treating a linear problem or non-linear problem.
No, everything is linear. So the non-linearity, there was just one slide about this, when I say that once you know the linear problem, then you can deal with the non-linear problem just iteratively by looking at this resonance, but everything else was linear.
So in that sense, why is this a generalized eigenfunction rather than just the eigenfunction?
Because usually people don't talk about eigenfunction if the energy is infinite. So for instance, I think you wouldn't say that exponential of ix psi is an eigenfunction of Laplacian on the Wool space. Because you cannot take the L2 norm of this, so you can take the energy of this. So generalized is just in the sense that it has infinite energy. And so especially you cannot say that you will decompose, of course you can decompose your, say, what you obtain is that you have really a continuous decomposition. So if maybe I can write something like this. Okay, so if you just think about Fourier in the Wool space, so of course you have this guy, if you take the Laplacian, will be minus xi squared exponential of. So in this sense here, this is an eigenfunction, but of course you cannot compute this guy. This is plus infinity. And now if you have say an initial data or a forcing which has finite energy, if you would like to decompose it on this eigenfunctions, say instead of having a finite sum or a countable sum, what you will have is a continuous sum. So what you get is something like u of x will be the sum of u of xi dxi, but you see that the xi here is in an interval, not discrete sum. So this is exactly this is really the thing that you should have in mind is really this continuous Fourier decomposition. It's exactly the same, except that now you have the same but in a finite box. And so the reason why so here the reason why the energy is infinite is just because you integrate 1 over something which is infinite. And here the reason why the energy of the eigenfunction here is infinite is that it behaves like 1 over x here, and 1 over x square is not integrable.
In the introduction, they said that you have worked also on the Boltzmann equation.
Yes.
Now, if in place of using Navier-Stokes equation, you use, if you want to use in a relativistic situation, for instance, for a neutron star, I don't know if how much of the formulation and techniques that you have described here can be applied. Have you ever tried to see, because this would be very interesting for people who want to look at neutron stars when gravity is very strong and you have to really consider all the relativistic correction and so on and so forth.
So what I would say is that there are two things. So in this lecture, what I try to do is to present some mathematical techniques. So this kind of tools, semi-classical, etc. So of course, they have counterparts at the relativistic. And so the techniques, if you have really one term which is dominating and you have waves and so on, you can say in principle there is no objection to use the same techniques for different models. Now, if, say, in the relativistic case, I think that all these models from fluid mechanics are probably not relevant because they rely on the assumption that somehow you have this, so I think that the Navier-Stokes equation are not relevant for this kind. So what I would say is that probably if you have waves, even waves coming from with different, say corresponding to different phenomena, there is no objection to use these methods, which are really a method for scale separation. So there is no objection to extend them to different problems. Here I started from this model because this is something that I know and I know how it works. But I don't think that you can say, except from really a strategy, I don't think that you can use any of this result as a black box. So essentially, you have to redo everything.
I'm a bit confused because if you're actually treating a linear problem, then how comes that you get energy cascade smaller scale? Because to achieve that, you need mode coupling, right?
If I add coupling in this problem here?
In some sense, we need mode coupling to get a cascade of energy to a small scale.
No, this is exactly what I told, is that here in this problem, because say somehow the interaction of with the boundary will generate the cascade even though you don't have any non-linearity. You have creation of small scales just because, say somehow you are focusing because just of the boundary. You don't need any non-linearity to generate small scales. I think it's really something which I know it's a little bit non-intuitive. It was the same for me, even though I'm not a physicist. But say the result here is that you can generate small scales just with the linear problem without any non-linearity. So that's why it's not really turbulence, because say when people talk about turbulence, what they have in mind in general is a nonlinear mechanism. But here what I say is that you can find the same kind of spectrum, the same kind of cascade to small scales, the same kind of cutoff due to viscosity, and all all these things, which are important feature from turbulence, you can find them with a linear model, which do like this.
So is it essentially because we don't have analytical equation as you showed here, you have distributions like what are written there. Is this the origin of this turbulence even in
the origin is really this mechanism here that each time a wave, say, if you think about in terms of waves, which is not completely correct because you cannot really think in terms of waves if you don't have a scale separation from the beginning. So, say it's not completely correct this picture, but it's really the counterpart of what we know for acoustic waves and so on. But what I say, what is responsible for this generation of small scales is this focusing and defocusing along the boundary. Yeah, this is really how you generate these small scales, starting from just something which is completely smooth.